Hello and welcome to Sparx Science for Sleep, a quiet little corner of the universe where science slips into its softest pajamas and curiosity hums a lullaby. I'm so glad you're here, maybe curled up in a cozy blanket or nestled on a couch, ready to unwind after a long day of being wonderfully human. Tonight, we're embarking on a dreamy journey through the story of the Big Bang, that first spark of everything. A moment so vast yet so gentle it feels like the universe whispering its own bedtime story. If you're listening from a far-off city or a quiet town, maybe leave a comment to share where you are, what time it is in your little slice of the night. Take a deep breath now, let it out slowly, and feel your body soften, your worries drifting away like clouds in a starry sky. This is a safe space, a place where science becomes a soft glow, guiding you toward peace, toward sleep. If you drift off, that's perfectly fine. The universe will carry you gently. If you stay awake, you'll uncover a few of its quiet wonders. Either way, you're right where you belong. Let's begin at the very start, with the spark of everything. Close your eyes, or soften your gaze, and imagine a moment before time, before space, before anything we can name. It's not darkness, not light, just a single point, smaller than a grain of sand, smaller than a whisper. This is where it all began, about 13.8 billion years ago, in a moment we call the Big Bang. Picture it like a tiny ember, glowing softly in an endless night, holding everything inside it, every star, every planet, every breath you've ever taken, all curled up in a space so small it's hard to imagine. Isn't it wild to think that everything you are, everything you love, was once tucked inside that one delicate spark? It's like the universe was humming a single note, a lullaby that would grow into a cosmic symphony. Take another slow breath and let your shoulders sink deeper into this moment. Scientists, those curious explorers of the cosmos, have found ways to listen to this ancient spark. They use something called the cosmic microwave background, a faint glow that's like the echo of the Big Bang, still lingering in the universe today. Imagine it as a soft hum, a ripple of light that's been traveling for billions of years, carrying the story of the universe's first moment. They catch this glow with telescopes, not the kind you point at stars, but special ones that listen to the sky's oldest whispers. It's like finding a letter written by the universe when it was just a baby, a note that says, "I'm here and I'm ready to grow." This glow tells us the Big Bang wasn't loud or chaotic, but a gentle unfolding, a quiet promise that set everything in motion. Feel yourself floating now, weightless, as if you're cradled by the universe itself. That tiny spark wasn't just a beginning, it was a gift. It held the potential for galaxies, for oceans, for the laughter of children, and the warmth of a summer night. Scientists think that in that first fraction of a second, time and space were born together, like twins holding hands. There were no stars yet, no planets, just a sea of energy, pure and radiant, like the first breath of a dream. Have you ever wondered what it would feel like to be there, at the edge of creation, watching the universe take its first step? It's a humbling thought, isn't it? That something so vast, so beautiful, could start so small, so simple, like a single note in a song that's still being written. Let your breath flow gently, in and out, like a tide lapping at a quiet shore. The Big Bang wasn't an explosion, not the way we think of fireworks or chaos. It was more like a bloom, a flower opening in slow motion, spreading light and possibility in every direction. Scientists study this moment with tools like math and imagination, piecing together clues from that ancient light. They've learned that the universe was hot back then, unimaginably hot, but also smooth and even, like a calm sea before the waves begin to form. And in that smoothness, there were tiny ripples, little whispers of difference that would one day become the seeds of stars and galaxies. It's like the universe was dreaming its own future, sketching out a map of everything to come. As you rest here, safe and warm, imagine yourself as a quiet witness to this beginning. You're not just hearing a story, you're part of it. The atoms in your body, the air in your lungs, they all trace back to that first spark. Isn't that a comforting thought? That you're connected to the universe in such a deep, quiet way? Science is like a lantern, lighting up these connections, showing us how we're woven into the fabric of everything. And as you breathe, slow and steady, You can feel that connection, like a thread tying you to the stars, to the vast, gentle cosmos. Now, let your mind drift softly, like a leaf on a calm river. We've touched the spark of everything, felt its warmth, its promise. But the universe didn't stay still. It began to stretch, to grow, to unfold into something even more wondrous. So let's float forward, just a little, to the next chapter of this cosmic story, where the universe begins to spread its wings and soar. Let's take a slow, deep breath now, letting it flow in and out like a gentle breeze across a quiet meadow. Feel your body soften, sinking deeper into this cozy moment, as if you're floating on a cloud, weightless and safe. We've just touched the spark of everything, that tiny ember where the universe began, humming its first note. Now, let's drift forward, ever so gently, to a time when that spark began to stretch, to grow, like a soft breath expanding into a vast, endless sky. Imagine yourself gliding through this young cosmos, where everything is new, where the universe is unfurling its wings for the very first time. It's a quiet, wondrous moment, and you're here, cradled in its warmth, ready to explore the next chapter of this cosmic lullaby. Picture the universe, just moments after its birth, still glowing, still impossibly small, but ready to become something grand. In a fraction of a secondless time than it takes to blink, the universe began to stretch, to swell, like a balloon softly filling with starlight. This is what scientists call cosmic inflation, a breathtaking moment when the cosmos grew faster than you can imagine, faster than light itself, in a gentle, graceful rush. It's as if the universe took a deep breath of its own, expanding from something smaller than a speck of dust to a vast, shimmering sea of possibility. Can you feel it? That sense of something small becoming boundless, like a dream that starts in a single thought and grows to fill your entire mind. Breathe in again, slow and steady, letting any tension melt away like mist in the morning sun. This cosmic stretch wasn't just about size, it was about setting the stage for everything we know. Scientists believe this rapid expansion happened in the tiniest sliver of time, something like a trillionth of a second. It's hard to wrap your mind around, isn't it? But don't worry, you don't need to grasp it all. Just imagine a soft, radiant wave, rippling outward, carrying the universe's first possibilities. This moment smoothed out the cosmos, like a painter gently brushing color across a canvas, creating a space where stars and galaxies could one day take shape. It's like the universe was preparing a home, a place for all its wonders to grow. As you rest here, safe and warm, picture yourself floating in this expanding cosmos, surrounded by a soft glow, like fireflies dancing in a twilight field. Scientists have puzzled over this moment for years, using math and telescopes to piece together its story. They've found clues in the way the universe looks today, in the patterns of galaxies scattered across the sky. Those patterns started here, in this gentle stretch, where tiny differences in the universe's fabric began to form. Think of it like ripples on a calm pond, so small you can barely see them, but each one destined to become something extraordinary. Maybe a star, maybe a planet, maybe the very air you're breathing now. Let your breath flow easily, like a river moving over smooth stones. These tiny ripples, these little whispers of difference, were the seeds of everything. During cosmic inflation, the universe didn't just grow, it stretched those ripples, spreading them across its vast new canvas. Scientists call these fluctuations, and they were so delicate, so subtle, like the faintest brushstrokes in a watercolor painting. But they were powerful too, because they would guide the universe's future. Each ripple was a hint, a quiet promise of the galaxies that would one day form, of the stars that would light up the night, of the planets that would cradle life. Isn't it beautiful to think that even in its earliest moments, the universe was already dreaming of you? Feel yourself sinking deeper into this moment, your body light, your mind drifting like a leaf on a quiet stream. Scientists study this cosmic stretch with tools that feel almost magical, like giant telescopes that peer back in time, catching light that's been traveling since the universe was young. They've learned that inflation wasn't just fast, it was perfectly balanced, creating a universe that's flat and smooth, like a sheet of paper stretched across the cosmos. This balance is why we have galaxies, why we have stars, why we have this moment right now, with you resting here, listening to the universe's story. It's as if the cosmos knew exactly how much to stretch, like a dancer moving in perfect rhythm, setting the stage for everything to come. Take another slow breath, letting it carry you deeper into calm. The universe, during this stretch, was still so young, still so hot, like a glowing ember cooling in the night air. But as it grew, it began to change. The energy that filled it started to shift, to settle, like a song moving from one note to the next. Scientists think that inflation was driven by a mysterious force, something they call the inflaton field. It's a strange name, isn't it? But imagine it as a gentle push, a soft wind that carried the universe outward, giving it room to breathe, to become. No one's quite sure what this field was, but it's like the universe's first sigh, a moment of expansion that made space for all the wonders we see today. As you float here, weightless in this cosmic sea, imagine the universe as a vast, shimmering tapestry, slowly unfurling. Those tiny ripples from before, they're still there, stretched across the cosmos like threads woven into the fabric of space. Scientists have found traces of these ripples in the cosmic microwave background, that same faint glow we talked about before. It's like the universe left a map of its childhood, a snapshot of those early moments when it was still growing, still stretching. By studying this map, scientists can see how the universe's structure began to form, how those tiny differences became the seeds of galaxies, of clusters, of the vast cosmic web that holds everything together. Let your eyelids grow heavy, your breath soft and even, like the tide lapping at a quiet shore. This moment of cosmic inflation is so strange, so wonderful, because it happened so quickly, yet left such a lasting mark. In less than a blink, the universe grew by a factor of billions, maybe more. It's like a single drop of water spreading to fill an entire ocean. And yet, it was so gentle, so precise, like a painter adding just the right touch of color to a canvas. Scientists use computers to model this moment, to imagine what it was like when the universe was just a baby, stretching out its arms for the first time. They found that this rapid growth explains why the universe looks the way it does, why it's so vast, so even, so ready to hold the stars. Feel your body relax even more, as if you're sinking into a warm, soft bed of starlight. The cosmic stretch wasn't just about making the universe bigger, it was about giving it shape, giving it possibility. Those tiny ripples, those subtle differences, were like the first notes in a cosmic melody, each one carrying the promise of something new. Scientists think these ripples came from quantum fluctuations, tiny wobbles in the fabric of reality itself. Can you imagine that? Even in the universe's earliest moments, there was a kind of dance, a playful shimmer of chance that would shape everything to come. It's like the universe was humming to itself, dreaming of the galaxies it would one day become. Breathe in deeply now, and let the air slip out slowly, carrying away any lingering thoughts. The beauty of this moment is that it's both vast and intimate. The universe was growing, stretching, but it was also preparing a place for you, for me, for every living thing. Those quantum fluctuations, those tiny ripples, were the first whispers of structure, the first hints of the cosmic architecture we see today. Scientists study these patterns with tools like the Planck satellite, which map the sky in exquisite detail, catching the faint glow of the universe's infancy. It's like looking at a photograph of the cosmos when it was just learning to walk, just beginning to dream. As you rest here, safe and calm, imagine yourself as part of this unfolding story. You're not just a listener, you're a piece of the cosmos, a thread in its vast tapestry. The atoms in your body, the thoughts in your mind, they all trace back to this moment when the universe stretched and grew, making room for everything. Isn't it comforting to think that you're connected to something so grand, yet so gentle? Science is like a lantern, shining light on these connections, showing us how we fit into the universe's quiet dance. And as you breathe, slow and steady, you can feel that dance, like a rhythm that's been playing since the beginning of time. Let your mind drift now, soft and easy, like a feather floating on a gentle wind. The universe, in this moment of stretching, was still so young, still so full of potential. It was like a canvas waiting for its first brushstrokes, a story waiting to be told. And as it grew, it began to cool, to settle, like a lake after a storm, ready for the next chapter. So, let's float forward, just a little, to a time when the universe begins to hum with new life, when the first tiny dances the particles of matter begin to twirl in the cosmic dawn. We've just glided through the universe's grand stretch, where it unfolded like a vast, shimmering tapestry, swelling with the promise of stars and galaxies. Now, the cosmos shifts to a new scene, a radiant, bustling haze where the first tiny particles begin to twirl, setting the stage for the universe's next act. This is the era of the quark-gluon plasma, a fleeting, vibrant moment when fundamental particles, quarks, electrons, and others moved in a warm, glowing dance, weaving the earliest threads of matter. The universe, only a fraction of a second old, was a fiery sea of energy, dense and hot, like the glow of a molten ember before it settles. Within this primal broth, the smallest building blocks emerged, quarks, tinier than a whisper, and electrons, charged with restless energy. These particles swirled in a state called the quark-gluon plasma, where matter and energy were so entwined they flowed as one, like a river of light and possibility. Quarks, the universe's smallest sparks, darted through this plasma, each one a seed of future protons and neutrons. Electrons, with their electric buzz, wove through the chaos, their movements hinting at the atoms they would one day form. This plasma was a unique state, a cosmic soup where the rules of matter were still forming. Gluons, carriers of the strong nuclear force, acted like invisible threads, linking quarks in fleeting partnerships. This force, one of nature's core laws, held quarks close, guiding their rapid, intricate motions. Electromagnetism, another fundamental force, gave electrons their lively spark, allowing them to interact and dance through the glowing haze. The universe was alive with activity, a bustling sea where particles collided, scattered, and reformed, each encounter a step toward the cosmos's future structure. Scientists recreate this era using particle accelerators, vast machines like the Large Hadron Collider, buried deep underground. These accelerators propel particles to near light speeds, then collide them, producing tiny bursts of energy that mimic the quark-gluon plasma. These experiments reveal how quarks and gluons moved in that early universe, offering a window into a time when the cosmos was trillions of degrees hot, yet remarkably fluid, like a molten sea flowing in harmony. The data shows a universe that was nearly uniform, with particles gliding together, their motions guided by the fundamental forces that shaped their dance. As the universe cooled just a millionth of a second after its birth, the quark-gluon plasma began to transform. Quarks, once free to roam, started to cluster, forming protons and neutrons. 3 quarks would bind together, held by gluons, to create a proton with its positive charge or a neutron, neutral and steady. This process, known as hadronization, marked the shift from a chaotic sea of particles to the first stable bits of matter. Protons and neutrons were the universe's earliest building blocks, the foundation for atoms that would one day form stars, planets, and life itself. Neutrinos, ghostly and elusive, were also part of this cosmic scene. These nearly massless particles slipped through the plasma, interacting so weakly they passed through matter-like shadows through a forest. Known as the universe's silent wanderers, neutrinos carried faint traces of the early cosmos, their paths barely disturbed by the chaos around them. Scientists capture these particles with massive detectors, often hidden in deep caves or beneath polar ice, to study their ancient signals. These detectors, like cosmic nets, collect neutrinos that have traveled billions of years, revealing secrets of the universe's particle-filled dawn. In this era, a delicate balance between matter and antimatter played a critical role. For every quark, there was an antiquark. For every electron, a positron antimatter twins with the same mass but opposite charge. When matter and antimatter met, they annihilated in a burst of pure light, vanishing completely. In the early universe, these pairs were nearly equal, locked in a cosmic duel. Yet, a tiny imbalancey one extra matter particle for every billion pairs allowed matter to prevail. This phenomenon, called baryon asymmetry, was the key to the universe's survival, ensuring that matter endured to form the cosmos we know. Scientists explore this mystery through experiments at facilities like CERN, where particle collisions hint at why matter outlasted antimatter. Some particles, like certain heavy quarks, may have decayed differently from their antimatter counterparts, creating a slight surplus of matter. The cosmic microwave background, that faint glow from the universe's infancy, shows patterns that support this imbalance, suggesting it was a subtle but deliberate shift. This surplus was like a single extra thread in a vast cosmic weave, essential to the tapestry of stars, galaxies, and life. As the universe continued to cool, the quark-gluon plasma faded, and protons and neutrons became the dominant players. The strong nuclear force, which bound quarks into these particles, now held protons and neutrons together, forming the seeds of future atoms. These particles were stable, like the first stones in a cosmic foundation, ready to build the universe's next structures. Scientists study this transition through computer simulations, modeling how the cosmos shifted from a fluid of particles to a place where matter could endure, laying the groundwork for everything to come. The dance of particles was a brief but pivotal moment, lasting less than a millionth of a second, yet it shaped the universe's future. Quarks, electrons, and neutrinos, guided by the strong nuclear force and electromagnetism, moved in a delicate balance, creating the first stable matter. Particle accelerators and neutrino detectors allow scientists to probe this era, revealing how the universe's earliest dancers set the stage for galaxies and stars. The survival of matter over antimatter, a puzzle still unfolding, was the spark that made the cosmos possible, connecting the smallest particles to the vastest wonders. Now, let's glide forward to a time when these particles begin to unite, when protons and electrons join to form the first atoms, casting a soft, radiant glow across the cosmic dawn. We've just glided through the vibrant dance of particles, where quarks and electrons swirled in a warm cosmic soup, laying the foundation for matter itself. Now, the universe shifts to a quieter, softer moment, like a dawn breaking after a long night. This is the era of recombination, when protons and electrons join to form the first atoms, casting a gentle glow across the cosmos. Picture a vast, cooling sea of light and matter, where the universe begins to clear, allowing beams of radiance to travel freely for the first time. The universe, now about 380,000 years old, was cooling from its fiery beginnings, its temperature dropping to a mere few thousand degrees, like a glowing ember settling into a soft warmth. In this calmer cosmos, protons and electrons, once too energetic to stay together, began to pair up. Protons, with their positive charge, and electrons, with their negative spark, were drawn to each other by electromagnetism, like partners finding each other in a slow, graceful waltz. Together, they formed the first hydrogen atoms, simple structures of one proton orbited by one electron, the universe's earliest building blocks. This moment, called recombination, was a turning point. Before, the universe was a dense fog of charged particles, scattering light in every direction, like a misty morning where you can't see far. Photons, the particles of light, were trapped, bouncing between protons and electrons, unable to travel freely. As the universe cooled, and protons and electrons united into neutral hydrogen atoms, the fog began to lift. Photons could now move without interruption, streaming across the cosmos in straight, unbroken paths. This was the universe's first sunrise, a moment when light broke free, painting the cosmos with a soft, radiant glow. Scientists study this era through the cosmic microwave background, the ancient light that began its journey during recombination. This light, now stretched and cooled by the universe's expansion, appears as a faint microwave glow across the sky. Telescopes like the Planck satellite capture this glow, mapping its subtle patterns to reveal the universe's state at 390,000 years old. These patterns show a cosmos that was almost perfectly uniform, with tiny variations less than 1 part in 100,000 that would later become the seeds of galaxies. The cosmic microwave background is like a snapshot of the universe's childhood, a photograph of its first clear moment. Hydrogen atoms dominated this era, but a small fraction of helium atoms formed too, each with 2 protons, 2 neutrons, and 2 electrons. These helium atoms, heavier and more complex, were like the first hints of diversity in the cosmic story. The formation of these atoms was governed by the delicate balance of temperature and density. Too hot, and the particles would scatter. Too cold, and they wouldn't interact. Recombination happened at just the right moment, like a note struck perfectly in a quiet melody, allowing the universe to transition from a charged, opaque haze to a transparent sea of neutral atoms. The cosmic microwave background carries more than just light. It holds clues about the universe's composition. By analyzing its spectrum, scientists learned that the early universe was about 75% hydrogen and 25% helium, with trace amounts of other elements like lithium. This mix, called the primordial abundance, matches predictions from Big Bang nucleosynthesis, a process we'll explore later, confirming that the universe's first atoms were born in this era. The precision of these measurements is astonishing, like reading the ingredients list of a cosmic recipe written billions of years ago. Telescopes like the Wilkinson Microwave Anisotropy Probe have mapped the cosmic microwave background in exquisite detail, revealing tiny temperature differences across the sky. These differences, like ripples in a calm pond, show where matter was slightly denser, where the seeds of future galaxies began to form. Scientists use these maps to understand the universe's early structure, piecing together how it evolved from a smooth, glowing sea to a cosmos filled with stars and planets. The light from recombination is a bridge to the past, connecting us to a time when the universe was young and just beginning to shine. Recombination also marked the end of the universe's plasma state, a phase where charged particles dominated. As neutral atoms formed, the cosmos became transparent, allowing light to travel vast distances without scattering. This transparency was crucial, as it set the stage for the universe to grow and organize. The newly formed atoms were stable, like the first bricks in a cosmic foundation, ready to be shaped by the forces that would come next. The universe was no longer a chaotic dance of particles, but a calmer, clearer space, poised for the next chapter of its story. The cosmic microwave background isn't just a scientific tool, it's a testament to the universe's evolution. Its light, which began as visible and ultraviolet during recombination, has been stretched by the universe's expansion into the microwave range. This stretching, called redshift, is like a cosmic echo, showing how far the universe has grown since its early days. Scientists measure this redshift to calculate the universe's age and expansion rate, confirming that it began 13.8 billion years ago. The cosmic microwave background is like a letter from the young universe, written in light, telling us about its first moments of clarity. The era of recombination was a quiet transformation, a shift from opacity to transparency, from chaos to order. The formation of hydrogen and helium atoms created a cosmos where light could roam free, illuminating the path for future structures. Scientists use supercomputers to simulate this era, modeling how particles came together and how light began to travel. These simulations show a universe in balance, with just enough matter and energy to allow atoms to form without collapsing or flying apart. It's like the universe found its rhythm, settling into a gentle harmony that would guide its growth. This moment also set the stage for the universe's large-scale structure. The tiny density variations in the cosmic microwave background, those faint ripples, were the seeds of galaxies, clusters, and filaments. As atoms formed, these variations became the blueprint for where matter would gather, like sketches on a cosmic canvas. Scientists study these patterns to understand how the universe evolved, using telescopes and mathematical models to trace the journey from a smooth, glowing sea to a cosmos filled with intricate structures. The light from recombination, now stretched into microwaves, is one of the most powerful tools in cosmology. It allows scientists to test theories about the Big Bang, measure the universe's composition, and estimate its age with remarkable precision. The cosmic microwave background is like a fossil, preserving the universe's early state, and its study has confirmed many predictions about the Big Bang model. It's a reminder that even the smallest moments in the universe's history can leave lasting echoes, guiding our understanding of the cosmos. As the universe became transparent, it entered a new phase, ready for the forces of nature to sculpt its future. The first atoms, mostly hydrogen with a sprinkle of helium, were simple but essential, like the first notes in a cosmic symphony. Their formation marked the end of the universe's opaque youth, and the beginning of a clearer, more structured era. Scientists continue to probe this moment, using the cosmic microwave background to uncover details about the universe's temperature, density, and expansion, piecing together the story of how it grew from a glowing haze to a vast, star-filled cosmos. Now, let's drift forward to a time when gravity begins to weave these atoms together, gathering them into clumps that will one day form the stars and galaxies of the cosmic night. We've just drifted through the era of recombination, where protons and electrons united to form the first atoms, clearing the cosmic fog and letting light stream freely across the universe. Now, the cosmos settles into a quieter phase, a vast, transparent sea of hydrogen and helium atoms, ready to be shaped by a gentle, invisible force. This is the time when gravity begins its patient work, gathering matter into delicate clumps, like a weaver threading stardust into the first sketches of galaxies. Picture a serene, expansive canvas where the universe starts to organize itself, setting the stage for the stars and galaxies that will soon light up the cosmic night. The universe, now hundreds of thousands of years old, was a calm expanse filled with neutral atoms, mostly hydrogen with a touch of helium, floating in a vast, cooling void. Gravity, one of nature's fundamental forces, began to act like a cosmic sculptor, tugging at these atoms with a subtle, persistent pull. Unlike the rapid chaos of the early universe, this era was slow and deliberate, as gravity worked to draw matter together. Tiny variations in density, those faint ripples left from the universe's infancy, became the focal points. Where matter was slightly denser, gravity's pull was stronger, coaxing atoms into clusters, like grains of sand gathering on a gentle slope. These density variations, first seen in the cosmic microwave background, were incredibly small differences of less than 1 part in 100,000. Yet, they were enough to guide gravity's hand. In regions where atoms were slightly more crowded, gravity pulled them closer, forming wispy clouds of gas. These clouds, known as primordial gas clouds, were the earliest seeds of structure, the precursors to galaxies. Over millions of years, gravity compressed these clouds, making them denser and hotter, like a quiet gathering of friends huddling closer in a cool evening breeze. This slow, patient process was the universe's first step toward building the intricate structures we see today. Scientists study this era through observations of the universe's large-scale structure, using telescopes to map the distribution of galaxies across the sky. These maps reveal how those early density variations grew into vast clusters, walls, and voids, showing gravity's role in shaping the cosmos. Computer simulations also help, modeling how gravity pulled matter together over millions of years. These simulations show a universe where small clumps of matter merged into larger ones, like streams joining to form rivers, each merger driven by gravity's gentle but relentless force. As gravity worked, the primordial gas clouds began to collapse under their own weight. The denser regions attracted more matter, growing into larger structures called dark matter halos. Dark matter, a mysterious substance that doesn't emit or absorb light, played a crucial role. It formed invisible scaffolds, like the framework of a house, around which hydrogen and helium atoms gathered. Scientists estimate that dark matter made up about 27% of the universe's mass energy at this time, providing the gravitational backbone for the formation of galaxies. Its presence amplified gravity's pull, helping gas clouds coalesce faster than they would have otherwise. Telescopes like the Hubble Space Telescope and the Atacama Large Millimeter Array capture light from the earliest galaxies, offering clues about this era. By observing distant objects, whose light has taken billions of years to reach us, scientists peer back to when gravity was just beginning to shape the cosmos. These observations show that the first structures were small, irregular clumps, far simpler than the grand spiral galaxies we see today. These clumps, often called proto-galaxies, were like the first rough sketches of a masterpiece, drawn by gravity's careful hand. The process of gravitational collapse was slow, taking millions of years, as the universe was still vast and matter was spread thin. In denser regions, gas clouds grew hotter as they compressed, their atoms colliding more frequently, like a crowd pressing closer in a quiet square. This heat prevented immediate collapse, creating a delicate balance between gravity's pull and the gas's resistance. Scientists study this balance through simulations, modeling how gas clouds evolved into denser structures. These models show that gravity's work was gradual, like a tide shaping a shoreline, patiently carving the universe's first forms. Dark matter's role was critical, as it didn't interact with light or heat, allowing it to clump more easily than ordinary matter. Its gravitational pull created wells in the fabric of space, where hydrogen and helium could gather. These dark matter halos were like cosmic cradles, nurturing the growth of the first stars and galaxies. Scientists infer dark matter's presence from its gravitational effects, seen in the motion of galaxies and the bending of light, a phenomenon called gravitational lensing. This lensing, where light from distant objects is warped by massive structures, reveals the invisible scaffolding that guided the universe's early structure. The cosmic microwave background, that ancient glow from recombination, also holds clues about gravity's early work. Its patterns show where matter was denser, where gravity began to pull atoms together. By analyzing these patterns, scientists calculate the universe's density and composition, confirming that ordinary matter, and dark energy together shaped its evolution. The ripples in the cosmic microwave background were like the first notes of a cosmic score, guiding gravity's composition of the universe's structure. As gravity gathered matter, the universe began to take on a new form. Small clumps merged into larger ones, forming proto-galaxies that would eventually grow into the galaxies we know. This process, called hierarchical clustering, was like a cosmic dance where smaller groups joined to form larger ensembles. Simulations show that these mergers were gentle, with clouds of gas blending over millions of years, their boundaries softening like waves merging in a calm sea. This slow aggregation was the foundation for the vast structures that would dominate the cosmos. Scientists also study the distribution of galaxies today to understand gravity's role in the early universe. Surveys like the Sloan Digital Sky Survey map millions of galaxies, revealing how they cluster in patterns shaped by those early density variations. These patterns, like a cosmic fingerprint, trace back to the moments when gravity began its work, pulling matter into the first clumps. The data shows a universe where gravity acted with precision, turning faint ripples into the seeds of massive structures. The era of gravitational collapse was a time of quiet transformation, as the universe moved from a smooth, transparent sea to a cosmos with the first hints of structure. The interplay between gravity and matter created a delicate balance, with dark matter providing the scaffolding and ordinary matter filling in the details. Scientists use a combination of observations, simulations, and theoretical models to explore this era, piecing together how the universe evolved from a diffuse gas to a place where stars could form. The first proto-galaxies were small, often just a few million times the mass of our Sunday, but they were the building blocks of the cosmos. Over time, these clumps would merge, grow, and collapse further, setting the stage for the birth of stars. The process was slow, as gravity worked patiently, like a craftsman shaping clay. Observations of distant galaxies, whose light has traveled billions of years, show these early structures as faint, irregular glows, like the first flickers of light in a darkened room. Gravity's role extended beyond individual clumps, shaping the universe's large-scale structure. The denser regions became the seeds of galaxy clusters, while less dense areas would become vast voids, empty of stars. This contrast, driven by gravity, created the blueprint for the cosmic web, a network of filaments, walls, and voids that defines the universe today. Scientists study this web through galaxy surveys and simulations, tracing how gravity sculpted the cosmos over billions of years. The interplay of gravity and matter was a delicate dance, with dark matter providing the invisible framework and hydrogen and helium filling in the visible details. The cosmic microwave background's ripples, amplified by gravity, became the seeds of this structure, guiding where matter would gather. Scientists used these observations to test theories of the universe's evolution, confirming that gravity was the primary force shaping its early growth, like a gentle hand guiding a river's flow. As gravity continued its work, the universe prepared for its next great act. The proto-galaxies, formed by the patient pull of gravity, were poised to collapse further, their gas clouds compressing until they ignited into the first stars. This moment, still millions of years away, would mark the universe's first true light, a beacon in the cosmic night. For now, gravity's quiet labor set the stage, gathering matter into the delicate clumps that would one day shine. Now, let's float forward to a time when these clumps begin to ignite, when the first stars spark to life, casting their gentle glow across the cosmic dawn. We've just floated through the era where gravity began its patient work, gathering atoms into delicate clumps, like a cosmic weaver threading stardust into the first sketches of galaxies. Now, the universe moves into a radiant new chapter, where these clumps ignite into the first stars, casting tiny flickers of light across the cosmic night. Picture a vast, dark canvas, slowly coming alive with glowing campfires, each one a beacon of creation, forging the elements that will one day build planets, oceans, and life itself. This is the birth of stars, a moment when the universe begins to shine with its own light, crafting the building blocks of everything we know. The universe, now roughly 200 million years old, was a sprawling expanse of hydrogen and helium gas, gathered into dense clouds by gravity's gentle pull. These clouds, nestled within dark matter halos, were like cosmic nurseries, where the conditions were just right for stars to form. As gravity compressed these clouds, their cores grew hotter and denser, like a quiet ember flaring into flame. When the temperature reached millions of degrees, a remarkable process began: nuclear fusion. This was the spark that ignited the first stars, known as Population 3 stars, the universe's earliest luminaries, glowing in a cosmos that had known only darkness. Nuclear fusion is the heart of a star's brilliance. In the crushing heat and pressure of a star's core, hydrogen atoms collide with such force that their nuclei merge, forming helium. This process releases a tremendous burst of energy, like a cosmic firework, powering the star's glow. Each fusion reaction transforms a small amount of mass into energy, following Einstein's famous equation, E equals mc squared. The energy pours out as light, heat, and radiation, traveling across the vastness of space. These first stars were massive, often hundreds of times larger than our Sun, their intense heat making them shine with a fierce, blue-white brilliance. These Population 3 stars were unique, born from a pristine mix of hydrogen and helium, with no heavier elements to cloud their composition. Unlike later stars, they contain no metal elements like carbon, oxygen, or iron, which astronomers call anything heavier than helium. Their purity made them burn hotter and faster, living short but brilliant lives, often just a few million years. As they fused hydrogen into helium, their cores began to produce heavier elements, like carbon and oxygen, through a series of fusion reactions. This was the universe's first alchemy, transforming simple atoms into the building blocks of planets and life. Scientists study these ancient stars through a combination of theory and observation, as their light is too faint to detect directly. Computer simulations model how these massive stars formed, showing how gravity collapsed gas clouds into dense, hot cores. Telescopes like the James Webb Space Telescope search for faint traces of these stars in the most distant galaxies, whose light has traveled billions of years to reach us. These observations reveal that Population 3 stars were not only bright, but also crucial, seeding the universe with the first heavy elements that would shape future generations of stars and planets. As these stars burned, their cores grew hotter, fusing helium into carbon, then oxygen, and, in their final moments, even heavier elements like neon and magnesium. The most massive stars ended their lives in spectacular explosions called supernovae, scattering these newly formed elements across the cosmos. These explosions were like cosmic fireworks, flinging carbon, oxygen, and other elements into space, where they would mix with gas clouds to form new stars and planets. This process, called nucleosynthesis, was the universe's way of crafting the ingredients for everything from mountains to living cells. Supernovae from these early stars were cataclysmic, releasing more energy in a moment than our Sun will emit in its entire lifetime. The shock waves from these explosions compressed nearby gas clouds, triggering the formation of new stars, like ripples spreading across a pond. The heavy elements they dispersed became the seeds for more complex structures, enriching the universe with the raw materials for planets, atmospheres, and even life. Scientists estimate that these first supernovae happened within a few 100 million years of the Big Bang, marking a turning point in the cosmic story. The light from these stars and their explosive deaths traveled across the universe, carrying the story of their creation. Some of this light is still detectable today, captured by powerful telescopes that peer back to the cosmic dawn. The James Webb Space Telescope, designed to detect infrared light, can see the faint glow of galaxies formed shortly after these first stars, offering clues about their size, brightness, and composition. These observations confirm that population 3 stars were massive and short-lived, their intense light ionizing the surrounding gas, stripping electrons from atoms and creating a new phase in the universe's evolution. This ionization, called reionization, transformed the cosmos once again. As the first stars shone, their ultraviolet light broke apart neutral hydrogen atoms, turning the universe back into a plasma of charged particles. This process cleared the cosmic fog, making the universe transparent again, much like it became during recombination. Reionization was a gradual process, lasting hundreds of millions of years, as more stars formed and their light spread. Scientists study this era through the light of distant quasars, whose spectra show how the universe transitioned from a neutral to an ionized state, revealing the impact of these first stars. The heavy elements from supernovae were critical for the universe's future. Unlike the pristine hydrogen and helium of population 3 stars, the next generation, known as population 2 stars, formed from gas clouds enriched with metals. These metals, though still a tiny fraction of the gas, allowed stars to form with less mass, living longer and burning cooler than their predecessors. This shift marked the beginning of a more diverse cosmos, where stars of different sizes and compositions could coexist, setting the stage for galaxies as we know them. Scientists use spectroscopy to study the light from these early stars, analyzing its wavelengths to identify the elements present. The spectra of distant galaxies show traces of carbon, oxygen, and other elements forged in the hearts of population 3 stars, confirming their role as cosmic alchemists. These observations, combined with simulations, show that the first stars formed in small, dense clumps, often within dark matter halos, just a few million times the mass of our Sunday. These clumps were the seeds of proto-galaxies, the earliest building blocks of the cosmic web. The birth of stars was a pivotal moment, not just for light but for the universe's chemical evolution. The heavy elements they produced, carbon, oxygen, nitrogen, and more, were like the first colors added to a blank canvas, giving the cosmos new depth and complexity. These elements would eventually form molecules, dust grains, and even the rocky cores of planets. Scientists study the oldest stars in our galaxy, known as metal-poor stars, to learn about this era. These stars, found in the Milky Way's halo, contain tiny amounts of metals, hinting at their connection to the first supernovae. The process of star formation was delicate, governed by a balance between gravity and the heat generated by collapsing gas clouds. As clouds compressed, their cores grew hotter, resisting further collapse until fusion ignited. This balance ensured that stars formed at just the right moment, like a note struck perfectly in a quiet melody. Simulations show that the first stars often formed in pairs or small clusters, their light merging to create a gentle glow in the cosmic night. These clusters were the earliest hints of galaxies, small but growing, as gravity continued to pull matter together. The first stars also played a role in shaping the universe's structure. Their radiation and supernovae created bubbles of ionized gas, like clearings in a cosmic forest. These bubbles grew and merged, transforming the universe into a patchwork of ionized and neutral regions. Scientists study this process through observations of high redshift galaxies, whose light has been stretched by the universe's expansion, shifting into the infrared. The James Webb Space Telescope is particularly adept at capturing this light, offering a window into the era when the first stars began to shine. The birth of stars was a slow, majestic process, unfolding over millions of years. Each star was a beacon, its light traveling across the cosmos, carrying the story of its creation. The heavy elements they forged were scattered by supernovae, enriching the gas clouds that would form new stars and planets. This cycle of birth, death, and rebirth was the universe's first rhythm, a quiet pulse that shaped its evolution. Scientists continue to probe this era, using telescopes, simulations, and theoretical models to understand how the first stars transformed the cosmos. As the universe filled with these early stars, it began to take on a new character. The dark, quiet expanse was now dotted with points of light, each one a testament to the universe's creativity. The heavy elements they produced laid the foundation for everything to come: planets, oceans, and even the carbon in our bodies. The first stars were the universe's pioneers, their brief but brilliant lives setting the stage for the galaxies that would soon form. Now, let's glide forward to a time when these stars begin to gather, when proto-galaxies form, swirling with starlight to create the cosmic cities of the universe's youth. We've just floated through the era where gravity began its patient work, gathering atoms into delicate clumps, like a cosmic weaver threading stardust into the first sketches of galaxies. Now, the universe moves into a radiant new chapter, where these clumps ignite into the first stars, casting tiny flickers of light across the cosmic night. Picture a vast, dark canvas slowly coming alive with glowing campfires, each one a beacon of creation, forging the elements that will one day build planets, oceans, and life itself. This is the birth of stars, a moment when the universe begins to shine with its own light, crafting the building blocks of everything we know. The universe, now roughly 200 million years old, was a sprawling expanse of hydrogen and helium gas, gathered into dense clouds by gravity's gentle pull. These clouds, nestled within dark matter halos, were like cosmic nurseries where the conditions were just right for stars to form. As gravity compressed these clouds, their cores grew hotter and denser, like a quiet ember flaring into flame. When the temperature reached millions of degrees, a remarkable process began: nuclear fusion. This was the spark that ignited the first stars, known as Population 3 stars, the universe's earliest luminaries, glowing in a cosmos that had known only darkness. Nuclear fusion is the heart of a star's brilliance. In the crushing heat and pressure of a star's core, hydrogen atoms collide with such force that their nuclei merge, forming helium. This process releases a tremendous burst of energy, like a cosmic firework, powering the star's glow. Each fusion reaction transforms a small amount of mass into energy, following Einstein's famous equation E equals mc squared. The energy pours out as light, heat, and radiation, traveling across the vastness of space. These first stars were massive, often hundreds of times larger than our Sun, their intense heat making them shine with a fierce, blue-white brilliance. These Population 3 stars were unique, born from a pristine mix of hydrogen and helium, with no heavier elements to cloud their composition. Unlike later stars, they contained no metal elements like carbon, oxygen, or iron, which astronomers call anything heavier than helium. Their purity made them burn hotter and faster, living short but brilliant lives, often just a few million years. As they fused hydrogen into helium, their cores began to produce heavier elements, like carbon and oxygen, through a series of fusion reactions. This was the universe's first alchemy, transforming simple atoms into the building blocks of planets and life. Scientists study these ancient stars through a combination of theory and observation, as their light is too faint to detect directly. Computer simulations model how these massive stars formed, showing how gravity collapsed gas clouds into dense, hot cores. Telescopes, like the James Webb Space Telescope, search for faint traces of these stars in the most distant galaxies, whose light has traveled billions of years to reach us. These observations reveal that Population 3 stars were not only bright, but also crucial, seeding the universe with the first heavy elements that would shape future generations of stars and planets. As these stars burned, their cores grew hotter, fusing helium into carbon, then oxygen, and, in their final moments, even heavier elements like neon and magnesium. The most massive stars ended their lives in spectacular explosions called supernovae, scattering these newly formed elements across the cosmos. These explosions were like cosmic fireworks, flinging carbon, oxygen, and other elements into space, where they would mix with gas clouds to form new stars and planets. This process, called nucleosynthesis, was the universe's way of crafting the ingredients for everything from mountains to living cells. Supernovae from these early stars were cataclysmic, releasing more energy in a moment than our Sunday will emit in its entire lifetime. The shockwaves from these explosions compressed nearby gas clouds, triggering the formation of new stars, like ripples spreading across a pond. The heavy elements they dispersed became the seeds for more complex structures, enriching the universe with the raw materials for planets, atmospheres, and even life. Scientists estimate that these first supernovae happened within a few 100 million years of the Big Bang, marking a turning point in the cosmic story. The light from these stars and their explosive deaths traveled across the universe, carrying the story of their creation. Some of this light is still detectable today, captured by powerful telescopes that peer back to the cosmic dawn. The James Webb Space Telescope, designed to detect infrared light, can see the faint glow of galaxies formed shortly after these first stars, offering clues about their size, brightness, and composition. These observations confirm that population 3 stars were massive and short-lived, their intense light ionizing the surrounding gas, stripping electrons from atoms, and creating a new phase in the universe's evolution. This ionization, called reionization, transformed the cosmos once again. As the first stars shone, their ultraviolet light broke apart neutral hydrogen atoms, turning the universe back into a plasma of charged particles. This process cleared the cosmic fog, making the universe transparent again, much like it became during recombination. Reionization was a gradual process, lasting hundreds of millions of years, as more stars formed and their light spread. Scientists study this era through the light of distant quasars, whose spectra show how the universe transitioned from a neutral to an ionized state, revealing the impact of these first stars. The heavy elements from supernovae were critical for the universe's future. Unlike the pristine hydrogen and helium of population 3 stars, the next generation, known as population 2 stars, formed from gas clouds enriched with metals. These metals, though still a tiny fraction of the gas, allowed stars to form with less mass, living longer and burning cooler than their predecessors. This shift marked the beginning of a more diverse cosmos, where stars of different sizes and compositions could coexist, setting the stage for galaxies as we know them. Scientists use spectroscopy to study the light from these early stars, analyzing its wavelengths to identify the elements present. The spectra of distant galaxies show traces of carbon, oxygen, and other elements forged in the hearts of population 3 stars, confirming their role as cosmic alchemists. These observations, combined with simulations, show that the first stars formed in small, dense clumps, often within dark matter halos just a few million times the mass of our Sunday. These clumps were the seeds of proto-galaxies, the earliest building blocks of the cosmic web. The birth of stars was a pivotal moment, not just for light but for the universe's chemical evolution. The heavy elements they produced, carbon, oxygen, nitrogen, and more were like the first colors added to a blank canvas, giving the cosmos new depth and complexity. These elements would eventually form molecules, dust grains, and even the rocky cores of planets. Scientists study the oldest stars in our galaxy, known as metal-poor stars, to learn about this era. These stars, found in the Milky Way's halo, contain tiny amounts of metals, hinting at their connection to the first supernovae. The process of star formation was delicate, governed by a balance between gravity and the heat generated by collapsing gas clouds. As clouds compressed, their cores grew hotter, resisting further collapse until fusion ignited. This balance ensured that stars formed at just the right moment, like a note struck perfectly in a quiet melody. Simulations show that the first stars often formed in pairs or small clusters, their light merging to create a gentle glow in the cosmic night. These clusters were the earliest hints of galaxies, small but growing, as gravity continued to pull matter together. The first stars also played a role in shaping the universe's structure. Their radiation and supernovae created bubbles of ionized gas, like clearings in a cosmic forest. These bubbles grew and merged, transforming the universe into a patchwork of ionized and neutral regions. Scientists study this process through observations of high redshift galaxies, whose light has been stretched by the universe's expansion, shifting into the infrared. The James Webb Space Telescope is particularly adept at capturing this light, offering a window into the era when the first stars began to shine. The birth of stars was a slow, majestic process, unfolding over millions of years. Each star was a beacon, its light traveling across the cosmos, carrying the story of its creation. The heavy elements they forged were scattered by supernovae, enriching the gas clouds that would form new stars and planets. This cycle of birth, death, and rebirth was the universe's first rhythm, a quiet pulse that shaped its evolution. Scientists continue to probe this era, using telescopes, simulations, and theoretical models to understand how the first stars transformed the cosmos. As the universe filled with these early stars, it began to take on a new character. The dark, quiet expanse was now dotted with points of light, each one a testament to the universe's creativity. The heavy elements they produced laid the foundation for everything to come: planets, oceans, and even the carbon in our bodies. The first stars were the universe's pioneers, their brief but brilliant lives setting the stage for the galaxies that would soon form. Now, let's glide forward to a time when these stars begin to gather, when proto-galaxies form, swirling with starlight, to create the cosmic cities of the universe's youth. We've just witnessed the birth of the first stars, their radiant campfires igniting the cosmic night, forging heavier elements that seeded the universe with the ingredients for life. Now, the cosmos shifts to a grander stage, where these stars begin to gather, swirling together to form the first galaxies, like cosmic cities aglow with starlight. Picture a vast, dark expanse coming alive with spiraling clusters, each a bustling hub of light and matter, weaving the universe's growing tapestry. This is the era when galaxies take shape, a time when the cosmos organizes itself into intricate, luminous structures, setting the foundation for the vast web of the universe. The universe, now several 100 million years old, was a sprawling canvas dotted with the first stars, their light piercing the darkness. These stars, born within dense clouds of hydrogen and helium, were not solitary for long. Gravity, ever patient, continued its work, pulling these stars and their surrounding gas into larger structures. These early gatherings, called proto-galaxies, were the seeds of the galaxies we know today, small clusters of stars and gas, held together by gravity's gentle embrace. Like villages forming in a quiet valley, these proto-galaxies began to merge, growing into larger, more complex systems, their stars swirling in delicate spiraling patterns. Proto-galaxies were small compared to modern galaxies, often containing just a few million stars, but they were vibrant hubs of activity. Within these clusters, new stars continued to form as gas clouds collapsed under gravity's pull, their cores igniting with nuclear fusion. The heavy elements from the first supernovae, like carbon and oxygen, enriched these gas clouds, allowing new stars to form with slightly different compositions. These second-generation stars, known as Population 2, were less massive than their predecessors, burning cooler and living longer, adding stability to the young galaxies. Scientists study these early galaxies using powerful telescopes like the Hubble Space Telescope and the James Webb Space Telescope, which capture light that has traveled billions of years. This light, redshifted into the infrared by the universe's expansion, reveals faint, irregular clumps proto-galaxies in their infancy. These observations show that early galaxies were chaotic, with stars forming rapidly in dense, turbulent clouds. Unlike the orderly spirals of modern galaxies, these early systems were more like scattered fireflies, their light blending into a soft, uneven glow. Gravity played a central role in shaping these galaxies, orchestrating their growth like a conductor leading a symphony. As proto-galaxies merged, their stars and gas began to orbit a common center, forming the first hints of structure. Some galaxies developed into elliptical shapes, like glowing orbs, while others began to spin into disks, the precursors to spiral galaxies like our Milky Way. This process, called hierarchical assembly, was a slow dance of mergers, with smaller clumps combining to form larger, more organized systems over millions of years. Dark matter, that invisible scaffold, was crucial in this era, Its gravitational pull held proto-galaxies together, providing the framework for stars and gas to gather. Dark matter halos, formed during the era of gravitational collapse, acted like cosmic anchors, keeping galaxies stable as they grew. Scientists infer dark matter's presence through its gravitational effects, seen in the rotation of galaxies and the bending of light from distant objects, a phenomenon called gravitational lensing. This lensing reveals the hidden mass of dark matter, showing how it guided the formation of galaxies. The early galaxies were also shaped by the intense activity of their stars. Supernovae from population 3 stars and the growing number of population 2 stars released powerful winds and radiation, pushing gas outward and triggering new star formation in nearby clouds. This feedback process, like a cosmic breeze stirring a quiet pond, regulated the growth of galaxies, preventing them from collapsing too quickly. Scientists study this feedback through simulations, modeling how gas, stars, and radiation interacted to shape the early universe's structure. Telescopes reveal that these early galaxies were often small, with diameters of just a few thousand light-years compared to the 100,000 light-years of our Milky Way. Yet, they were incredibly active, with stars forming at a rapid pace, fueled by the abundant gas. The light from these galaxies, captured by the James Webb Space Telescope, shows a universe alive with star formation, its galaxies glowing like scattered lanterns in the cosmic night. These observations confirm that galaxies formed within a few 100 million years of the Big Bang, marking a key milestone in the universe's evolution. The formation of galaxies was not uniform across the cosmos. In regions where matter was denser, galaxies grew faster, forming clusters that would later become massive hubs of light and matter. In less dense areas, galaxies remained small, scattered like quiet outposts in the vast void. This variation, rooted in the tiny density fluctuations from the cosmic microwave background, created a diverse cosmic landscape. Scientists map this landscape using galaxy surveys, like the Sloan Digital Sky Survey, which reveal how galaxies are distributed across the universe, tracing their origins back to this era. The interplay of gravity, dark matter, and star formation gave galaxies their unique shapes and sizes. Some became elliptical galaxies, packed with stars in a smooth spherical glow, while others formed disks, with stars orbiting in graceful spirals. The mergers of proto-galaxies were often violent, with gas clouds colliding and sparking bursts of star formation. Yet the process was gradual, unfolding over millions of years. Simulations show that these mergers were like rivers joining to form a larger stream, blending stars and gas into cohesive systems. Spectroscopy, the study of light's wavelengths, allows scientists to analyze the composition of these early galaxies. The spectra reveal traces of heavy elements carbon, oxygen, nitrogen forged in the first stars and scattered by their supernovae. These elements, though only a tiny fraction of the gas, were critical as they helped cool the gas clouds, making it easier for new stars to form. This cooling process, driven by the radiation of heavy elements, allowed galaxies to grow more efficiently, like a garden flourishing with the right nutrients. The early galaxies were also influenced by the universe's reionization, a process driven by the first stars. Their ultraviolet light ionized the surrounding hydrogen, creating bubbles of charged gas that expanded and merged, clearing the cosmic fog. This reionization, lasting hundreds of millions of years, shaped the environment in which galaxies formed, making the universe transparent again. Scientists study this process through the light of distant quasars, whose spectra show how the universe transitioned from neutral to ionized, revealing the impact of early galaxies. The growth of galaxies was a dynamic process, with mergers, star formation, and feedback from supernovae, creating a complex interplay. Some galaxies grew massive, hosting billions of stars, while others remained small, with just a few million. These differences, rooted in the initial density variations, created a rich diversity of galactic forms. Scientists use computer simulations to model this process, showing how galaxies evolved from small, chaotic clumps to the structured systems we see today, like the spiral arms of our Milky Way. Observations of high redshift galaxies, whose light has traveled billions of years, offer a window into this era. The James Webb Space Telescope captures these galaxies as faint, red smudges, their light stretched by the universe's expansion. These images show galaxies forming in clusters, their stars and gas swirling together like lanterns gathering in a cosmic city. The data confirms that galaxies began forming within 500 million years of the Big Bang, a testament to gravity's relentless work in shaping the cosmos. The formation of galaxies marked a new chapter in the universe's story, as the cosmos transitioned from a scattering of stars to organized, luminous systems. The interplay of gravity, dark matter, and star formation created a diverse array of galaxies, each a unique hub of light and matter. Scientists continue to study this era, using telescopes, simulations, and spectroscopy to uncover how these cosmic cities took shape, revealing the intricate processes that built the universe we know. As galaxies formed, they began to connect, their light and gravity weaving together to form the vast web of the cosmos. This network, still in its infancy, would grow into the intricate structure that defines the universe today, a tapestry of filaments, walls and voids, glowing with the light of countless stars. Now, let's zoom out to see this vast web take shape, where galaxies join to form a cosmic quilt, stitched together by the gentle threads of gravity. We've just watched galaxies take shape, swirling into cosmic cities aglow with starlight, as the universe organized its first clusters of stars and gas. Now, let's zoom out to behold a grander vista, where these galaxies weave together into a vast, intricate structure, like a cosmic quilt stitched by gravity. Picture a sprawling tapestry of light and matter, with glowing threads stretching across the cosmos, connecting galaxies in a delicate network of filaments, walls, and voids. This is the era of the cosmic web, a time when the universe's large-scale structure emerges, revealing a breathtaking pattern that binds the cosmos into a harmonious whole. The universe, now 1 billion years old, was no longer a scattered collection of stars and galaxies, but a complex, interconnected framework. Gravity, working tirelessly over hundreds of millions of years, had pulled galaxies into clusters, and these clusters into larger structures known as superclusters. These superclusters formed along dense threads called filaments, like glowing rivers winding through the cosmic landscape. Between these filaments lay vast, empty regions called voids, where matter was sparse, and walls-thin sheets of galaxies bridged the gaps, creating a three-dimensional network that spans billions of light-years. This cosmic web, as scientists call it, is the universe's large-scale architecture, a pattern shaped by the interplay of gravity and the initial density fluctuations from the Big Bang. Those tiny ripples in the cosmic microwave background, so faint they were barely detectable, had grown under gravity's influence into the seeds of this vast structure. In regions where matter was denser, galaxies clustered tightly, forming the bright nodes of the web. In less dense areas, voids expanded, creating vast, dark expanses where few stars shone. This contrast, rooted in the universe's earliest moments, gave the cosmos its intricate, web-like form. Scientists map this cosmic web using galaxy surveys, like the Sloan Digital Sky Survey, which catalogues millions of galaxies across the sky. These surveys reveal a universe organized into filaments that stretch hundreds of millions of light-years, connecting clusters and superclusters like threads in a cosmic tapestry. Walls, thinner and flatter, form sheets of galaxies, while voids, some spanning over 1 billion light-years, are nearly empty, like quiet clearings in a vast forest. These observations show that the cosmic web is not random, but a direct result of the universe's initial conditions, amplified by gravity's patient sculpting. Dark matter played a pivotal role in forming the cosmic web. Its invisible halos, which surrounded galaxies and clusters, acted like gravitational anchors, drawing ordinary matter into their embrace. Dark matter filaments, denser than the surrounding space, formed the backbone of the cosmic web, guiding galaxies into their positions. Scientists study dark matter's influence through gravitational lensing, where the light from distant galaxies is bent by massive structures, revealing the hidden presence of dark matter. This lensing, like a cosmic magnifying glass, shows how dark matter's gravity shaped the web's intricate pattern. Computer simulations are another key tool, modeling how the cosmic web evolved over billions of years. These simulations start with the density fluctuations seen in the cosmic microwave background, and trace how gravity pulled matter into filaments, walls, and voids. They show a universe where galaxies flow along filaments, like beads on a string, gathering at nodes where clusters and superclusters form. Voids, meanwhile, expand as matter is pulled away, creating vast, empty spaces. These models confirm that the cosmic web began forming within 1 billion years of the Big Bang, a testament to gravity's relentless work. The filaments of the cosmic web are the universe's highways, channeling galaxies and gas across vast distances. Some filaments span hundreds of millions of light years, their glowing threads made of countless galaxies, each a hub of stars and gas. These filaments are not static, they are dynamic, with galaxies moving along them, drawn by gravity toward denser regions. Scientists observe this motion through redshift measurements, which show how galaxies shift in response to gravitational pulls, like boats drifting along a cosmic current. Voids, the empty regions between filaments, are just as crucial to the cosmic web. These vast expanses, sometimes called cosmic deserts, contain far fewer galaxies, stars, or gas clouds than the filaments or walls. Yet, they are not entirely empty. Faint traces of gas and dark matter linger, stretched thin by the universe's expansion. Scientists study voids to understand the universe's growth, as their size and distribution reveal how matter was redistributed over time. Observations show that voids can be enormous, with some spanning over 1 billion light years, their emptiness a stark contrast to the glowing filaments. Walls, the thinner sheets of galaxies, form a delicate bridge between filaments and voids. These structures are like cosmic curtains draped across the universe, with galaxies scattered across their surfaces. Scientists find that walls are less dense than filaments but more populated than voids, creating a transitional layer in the cosmic web. Surveys like the 2DF Galaxy Redshift Survey map these walls, showing how they connect the universe's denser regions, like threads weaving a quilt together. The cosmic web is not just a structure, but a dynamic system, evolving as the universe expands. Galaxies within filaments and clusters continue to merge, drawn together by gravity, while voids grow larger as matter is pulled away. This evolution, observed through galaxy surveys and simulations, shows a universe in constant motion, yet balanced, with each part of the web playing a role. The cosmic web's pattern is like a cosmic fingerprint, unique to our universe, reflecting the initial conditions set by the Big Bang. Telescopes like the Hubble Space Telescope and the upcoming Vera C. Rubin Observatory provide detailed views of the cosmic web, capturing the light of distant galaxies to map its structure. These observations reveal that filaments, walls, and voids are interconnected, forming a network that spans the observable universe. The light from these galaxies, often redshifted by billions of years of travel, shows how the web formed, with early galaxies clustering along filaments and spreading into walls over time. Dark matter's role in the cosmic web cannot be overstated. Its gravitational pull created the framework for the web, guiding ordinary matter into place. Scientists study dark matter through its effects on galaxy motion and light, using techniques like weak gravitational lensing to map its distribution. These studies show that dark matter forms a skeleton for the cosmic web, with filaments, walls, and voids shaped around its invisible structure. This skeleton, though unseen, is the foundation for the universe's large-scale architecture. The cosmic web also influences the formation of new stars and galaxies. Within filaments, the dense gas clouds fuel rapid star formation as gravity compresses matter into new stellar nurseries. Clusters, where filaments intersect, are hotspots of activity, with galaxies colliding and merging, sparking bursts of star formation. Scientists observe these regions through X-ray telescopes, which detect the hot gas in clusters, and radio telescopes, which capture the faint glow of gas in filaments, revealing the dynamic processes at work. The cosmic microwave background, that ancient light from recombination, provides a blueprint for the cosmic web. Its tiny density fluctuations, amplified by gravity, became the seeds of filaments, walls, and voids. Scientists analyze these fluctuations to understand how the web formed, using their patterns to test theories of the universe's evolution. The cosmic microwave background's data confirms that the web structure is a direct result of the Big Bang's initial conditions, a testament to the universe's interconnected design. The cosmic web's formation was a slow, majestic process, unfolding over billions of years. Early galaxies, formed from the first stars, clustered along filaments, their light blending into glowing threads. Walls emerged as galaxies spread into thinner sheets, while voids expanded as matter was drawn away. This process, driven by gravity and dark matter, created a universe that is both vast and intricate, with each galaxy a part of a larger, harmonious whole. Scientists continue to study the cosmic web using a combination of observations, simulations, and theoretical models. Surveys like the Dark Energy Survey map the distribution of galaxies and dark matter, revealing how the web has evolved over time. These studies show a universe where gravity and expansion work in tandem, shaping a structure that is both dynamic and balanced, like a cosmic dance that never ends. As the cosmic web took shape, it became the universe's defining feature, a network that connects every galaxy, star, and planet. Its filaments, walls, and voids are like the threads of a quilt, each part contributing to the whole. The web's beauty lies in its scale and complexity, a structure that began with the faintest ripples and grew into a tapestry that spans billions of light years. Now, let's drift forward to reflect on the universe today, where mysterious forces like dark matter and dark energy guide the cosmic dance, gently pushing galaxies apart as the cosmos continues to evolve. We've just soared through the formation of the cosmic web, a vast quilt of filaments, walls, and voids, stitched together by gravity's patient hand, connecting galaxies in a luminous network. Now, let's settle into the present, gazing upon the universe as it exists today, a sprawling tapestry of stars, galaxies, and mysterious forces. Picture a cosmos in gentle motion, guided by unseen influences like dark matter and dark energy, which shape its quiet dance across billions of years. This is the modern universe, a place of breathtaking complexity, where the echoes of the Big Bang still resonate, and new mysteries unfold like a soft breeze nudging galaxies apart. The universe today, 13.8 billion years after its birth, is a vast expanse filled with hundreds of billions of galaxies, each home to countless stars and planets. These galaxies, from spirals like our Milky Way to massive ellipticals, are scattered across a cosmos that continues to expand. The expansion, first set in motion by the Big Bang, is not slowing but accelerating, driven by a mysterious force called dark energy. This force, like an invisible current, gently pushes galaxies farther apart, stretching the fabric of space itself. Scientists estimate that dark energy makes up about 68% of the universe's total energy, a dominant presence that shapes its fate. Dark matter, another enigmatic force, accounts for roughly 27% of the universe's mass energy. Unlike ordinary matter, which forms stars, planets, and gas clouds, dark matter does not emit, absorb, or reflect light, making it invisible to most telescopes. Yet, its gravitational pull is profound, holding galaxies and clusters together, like an unseen scaffold supporting a grand structure. Scientists detect dark matter through its effects on visible matter, such as the way galaxies rotate. Stars at the edges of galaxies move faster than expected, suggesting an invisible mass dark matter adds the extra gravity needed to keep them in orbit. The remaining 5% of the universe is ordinary matter, the atoms that make up everything we can: sea stars, planets, gas, and dust. This matter, forged in the hearts of the first stars and scattered by their supernovae, is a small but vital part of the cosmic recipe. The interplay of dark matter, dark energy, and ordinary matter creates the universe's delicate balance, a dance where each component plays a role. Scientists study this balance through observations of galaxy clusters, supernovae, and the cosmic microwave background, piecing together how these forces shape the cosmos. Dark energy's discovery came from observing distant supernovae in the late 1990s. Astronomers noticed that these exploding stars, used as cosmic distance markers, were farther away than expected, indicating that the universe's expansion was speeding up. This acceleration, driven by dark energy, was a surprise, as scientists had assumed gravity would slow the expansion over time. Dark energy acts like a repulsive force, countering gravity's pull, and its presence explains why galaxies are moving apart faster today than in the early universe. It's like a gentle breeze, nudging the cosmos to grow ever larger. Scientists explore dark energy through surveys like the Dark Energy Survey, which maps the positions and movements of galaxies to understand how this force influences the universe's expansion. These surveys show that dark energy is uniform across space, acting consistently no matter where you look. Its nature remains a mystery. Some theories suggest it's a property of space itself, while others propose it's a new kind of field, like a cosmic fluid. Whatever it is, dark energy is the dominant driver of the universe's expansion, shaping its future over billions of years. Dark matter, though invisible, reveals itself through gravitational lensing, where light from distant galaxies is bent by massive objects, like galaxy clusters rich in dark matter. This bending creates distorted images, like arcs or rings, allowing scientists to map dark matter's distribution. Observations show that dark matter forms halos around galaxies, anchoring them within the cosmic web's filaments and clusters. These halos, invisible yet massive, provide the gravitational glue that keeps galaxies from flying apart as they rotate. The cosmic microwave background, that ancient glow from the era of recombination, continues to offer clues about the modern universe. Its tiny temperature fluctuations reveal the proportions of dark matter, dark energy, and ordinary matter, confirming that the universe is flat, meaning light travels in straight lines on large scales. This flatness, a result of the precise balance of matter and energy, suggests the universe is finely tuned, a delicate equilibrium set by the Big Bang. Scientists use these measurements to calculate the universe's age, size, and expansion rate, painting a detailed picture of its current state. Galaxies today are diverse, ranging from small dwarfs with a few million stars to massive giants with trillions. Our Milky Way, a spiral galaxy about 100,000 light-years across, is home to roughly 200 billion stars, including our Sun. These galaxies continue to evolve, merging with others and forming new stars, though at a slower pace than in the early universe. Scientists study galaxy evolution through telescopes like the Hubble Space Telescope, which capture images of galaxies at different stages, showing how they grow, merge, and change over time. Supernovae, the explosive deaths of massive stars, remain key tools for studying the universe. Their brightness allows astronomers to measure vast distances, while their spectra reveal the elements they produce, like iron and silicon, which enrich the cosmos. Type Ia supernovae, which explode with consistent brightness, are especially useful as standard candles for measuring cosmic distances. These measurements helped confirm dark energy's role in accelerating the universe's expansion, a discovery that reshaped our understanding of the cosmos. The universe's expansion is not uniform. Gravity still pulls galaxies together in dense regions, forming clusters and superclusters. These structures, part of the cosmic web, are the largest gravitationally bound objects in the universe. Clusters, containing hundreds to thousands of galaxies, are filled with hot gas that emits X-rays, detectable by telescopes like the Chandra X-ray Observatory. These observations reveal the dynamics of clusters, showing how gravity and dark matter shape their growth, even as dark energy pushes the universe apart. Dark matter's particles remain a mystery. Some theories suggest they are weakly interacting massive particles, or WIMPs, which rarely interact with ordinary matter. Experiments deep underground, like those at the Large Underground Xenon Detector, search for these particles by detecting their faint interactions. Other theories propose dark matter could be axions, tiny particles with even less interaction. While no direct detection has been made, dark matter's gravitational effects are undeniable, shaping the universe's structure from galaxies to the cosmic web. The universe's fate hinges on dark energy's behavior. If it remains constant, the universe will continue to expand forever, with galaxies drifting farther apart until stars burn out and the cosmos grows cold and dark, a scenario called the Big Freeze. If dark energy strengthens, it could tear galaxies, stars, and even atoms apart in a big rip. Alternatively, if dark energy weakens, gravity might dominate, causing the universe to collapse in a big crunch. Scientists study the expansion rate through supernovae and galaxy surveys to predict which path the universe might take, though the answer remains uncertain. The cosmic microwave background also reveals the universe's geometry. Its flatness suggests a balance between the density of matter and the expansion driven by dark energy. This balance, precise to within a fraction of a percent, is a remarkable feature of the modern universe, hinting at the conditions set by the Big Bang. Scientists use this data to test theories like inflation, which propose that the universe's rapid early expansion smoothed out its structure, creating the flat, uniform cosmos we see today. Galaxies today are not just static structures. They are dynamic, with stars forming, dying, and recycling their material into new generations. In spiral galaxies like the Milky Way, star formation occurs in dense clouds along spiral arms, fueled by gas and dust enriched with heavy elements. Elliptical galaxies, often the result of mergers, have less gas and form fewer stars, appearing as smooth, glowing orbs. Scientists study these differences through spectroscopy, analyzing the light from galaxies to understand their composition, age, and history. Black holes, formed from the collapse of massive stars or the mergers of galaxies, are another feature of the modern universe. Supermassive black holes, millions to billions of times the Sun's mass, reside at the centers of most galaxies, including our own. Their immense gravity influences the motion of stars and gas, shaping galactic structure. The Event Horizon Telescope has captured images of black holes, like the one in the galaxy M87, revealing their shadowy silhouettes against glowing disks of gas, a testament to their power in the cosmos. The universe today is also filled with cosmic phenomena like quasars, powered by supermassive black holes devouring gas and dust. These objects, among the brightest in the universe, emit intense light and radio waves, visible across billions of light years. Quasars were more common in the early universe, but some still shine today, offering insights into galaxy evolution and black hole growth. Scientists study their spectra to learn about the gas and dust in their host galaxies, tracing the history of cosmic structures. The interplay of dark matter, dark energy, and ordinary matter creates a universe that is both vast and dynamic. Dark matter holds galaxies together, while dark energy drives them apart, a delicate balance that has shaped the cosmos over billions of years. Scientists use a range of tools, telescopes, simulations, and particle detectors to explore this balance, uncovering the mysteries of the universe's composition and fate. The modern universe, with its galaxies, stars, and unseen forces, is a testament to the Big Bang's legacy, a cosmos still unfolding in a quiet, majestic dance. Now, let's drift gently toward a final reflection, where the universe's vast beauty wraps around us, cradling our thoughts as we ease into the cosmic night. We've just gazed upon the universe today, a vast tapestry of galaxies, stars, and unseen forces like dark matter and dark energy, gently guiding the cosmos in its quiet, endless dance. Now, let's drift into a final, soothing reflection, wrapping ourselves in the wonder of this cosmic journey, from the Big Bang's first spark to the intricate beauty of the universe we know. Picture yourself floating in a serene, starlit expanse, where the echoes of creation hum softly, cradling your thoughts in a lullaby of light and mystery. This is our conclusion, a gentle farewell that ties together the universe's story, inviting you to rest in its embrace as you slip towards sleep. Take a slow, deep breath and let it flow out like a soft wave, easing you into calm. We began this journey with a single glowing spark, a moment so small yet so vast that it birthed time, space, and everything within them. That spark, the Big Bang, was the universe's first heartbeat, a whisper of creation that set the cosmos in motion. We floated through its rapid stretch, where the universe unfurled like a shimmering sail, spreading possibility across an endless sea. Then, we watched tiny particles dance in a warm, glowing soup, quarks and electrons twirling to form the first seeds of matter. Those particles united into atoms, clearing the cosmic fog and letting light stream freely, like a sunrise painting the heavens. Feel your body soften, sinking deeper into this peaceful moment. Gravity, patient and persistent, gathered those atoms into delicate clumps, setting the stage for the first stars to ignite, their campfires blazing in the cosmic night. Those stars forged heavier elements, scattering them across the universe, crafting the building blocks of planets and life. From there, galaxies took shape, swirling into cosmic cities aglow with starlight, their beauty revealed by telescopes that peer into the depths of time. These galaxies wove together into a vast cosmic web, a quilt of filaments, walls, and voids, stitched by gravity's steady hand. And today, we see a universe alive with motion, shaped by dark matter's invisible pull and dark energy's gentle push, a cosmos that continues to expand, evolve, and hum with mystery. The story of the Big Bang is more than a tale of science. It's a reminder of how everything is connected. The atoms in your breath, the stardust in your bones, all trace back to that first spark, those first stars, those first galaxies. The universe has been telling its story for 8 billion years, and you are a part of it, a quiet note in its grand symphony. Scientists have unraveled this story with tools like telescopes, particle accelerators, and simulations, each discovery a lantern illuminating the cosmos's past. The cosmic microwave background, that ancient glow, carries the universe's earliest memories, while galaxy surveys map its present, showing how far it has come. Let your thoughts drift softly, like leaves on a calm stream. The universe's journey is one of wonder, from a single point to a cosmos filled with billions of galaxies, each home to countless stars. The first stars, those blazing pioneers, lived brief but brilliant lives, their explosions seeding the universe with carbon, oxygen, and iron elements that now form the mountains, oceans, and even the cells in your body. Galaxies, born from gravity's patient work, grew into spirals, ellipticals, and irregular clusters, their light traveling billions of years to reach us. The cosmic web, with its glowing filaments and vast voids, is a testament to the universe's complexity, a structure that began with the faintest ripples and grew into a tapestry spanning billions of light years. The modern universe, with its mysterious dark matter and dark energy, is a place of balance and motion. Dark matter holds galaxies together, its invisible gravity anchoring the cosmic web, while dark energy pushes the universe to expand faster, like a breeze carrying ships across an endless sea. Scientists study these forces through observations of supernovae, galaxy clusters, and the cosmic microwave background, piecing together the universe's composition and fate. The universe is flat, they've found, its geometry a delicate balance of matter and energy, set by the conditions of the Big Bang. This balance suggests a cosmos finely tuned, a place where life could emerge, where stars could shine, where stories like ours could unfold. As you rest here, imagine the universe as a vast glowing ocean, its waves carrying the light of countless stars. Telescopes like Hubble and the James Webb Space Telescope capture this light, showing us galaxies as they were billions of years ago when the universe was young. These images are like letters from the past, written in starlight, telling us how the cosmos grew from its first spark to the intricate web we see today. The cosmic microwave background, with its subtle patterns, reveals the universe's infancy, while galaxy surveys map its present, showing how gravity and dark energy have shaped its evolution. The universe's story is one of transformation, from a single point to a cosmos filled with wonders. The first atoms, formed in the era of recombination, were simple, yet they carried the potential for everything we know. Gravity gathered them into clouds, which collapsed into stars, which forged the elements that built planets. Those stars clustered into galaxies, which wove together into the cosmic web, a structure that connects every corner of the universe. Dark matter and dark energy, though mysterious, are part of this story, guiding the cosmos in its quiet expansion, like unseen currents in a vast river. Scientists continue to explore this story, using every tool at their disposal. Particle accelerators recreate the conditions of the early universe, revealing how quarks and electrons danced in the cosmic dawn. Telescopes capture the light of distant galaxies, showing how they formed and evolved. Simulations model the growth of the cosmic web, tracing the interplay of gravity, matter, and energy. Each discovery adds a new chapter to the universe's tale, a tale that began with a spark and continues to unfold. billions of years later, in the galaxies we see, the stars that shine, and the planets that harbor life. The beauty of this journey is its vastness, yet its intimacy. The universe is immense, stretching billions of light years, yet it is connected to you, to the air you breathe, to the thoughts you carry. The elements in your body were forged in the hearts of ancient stars, scattered by their explosions, and gathered into the planet you call home. The cosmic web, with its glowing filaments, is a reminder that everything is linked, from the smallest particle to the largest galaxy. Science, with its telescopes and equations, is a way of listening to this connection, of hearing the universe's quiet song. As you linger in this moment, let the universe's story wrap around you, like a soft blanket of starlight. The Big Bang was not just a beginning, it was a promise, a moment that set everything in motion. From that spark came particles, atoms, stars, and galaxies, each step a part of the cosmic dance. The universe today, with its mysteries of dark matter and dark energy, is still evolving, still expanding, still telling its story. You are part of that story, a quiet, beautiful note in a symphony that has played for billions of years. If this journey has stirred your curiosity, or if it has simply lulled you towards sleep, know that you've traveled through the cosmos tonight. From the spark of the Big Bang to the vast web of galaxies, you've seen the universe unfold, its wonders revealed in gentle, glowing steps. If you enjoyed this quiet voyage, consider leaving a comment to share where you're listening from, what time it is in your corner of the night. Your thoughts are like stars, adding light to this cosmic tale. A like or subscription would warm this sleepy scientist's heart, helping this little channel grow, like a galaxy gathering new stars. Now, let the universe's lullaby carry you. The stars are shining, the galaxies are swirling, and the cosmos is humming its ancient song. Let your thoughts drift among the stars, where the Big Bang's echo still lingers, soft and eternal. Sleep well, my friend, and let the universe cradle you in its gentle, starry embrace. Good night.